This is, I think, something that's been said in the context of SETI for a long time, that this is a unique moment in history. But at the risk of kind of reiterating a cliche, I'm going to say it again, because I think it really is a very, very unique moment in history, in the history of humanity and in the history of SETI. We've never been more certain that all the things that we think are necessary for life to exist elsewhere in the galaxy are present in abundance. We know there's lots and lots of water. We know there's lots and lots of organic molecules and organic chemistry. All of the things that were present on the Earth and in our own solar system when life arose here about 4 billion years ago are present all over the place in our galaxy. And just recently we learned something very, very important that might have been somewhat obvious from kind of a Copernican standpoint. There are lots and lots of planets out there. Something like probably 95 or 99% of all the stars in our galaxy have a planet. And some significant fraction of those, maybe 5%, maybe 20%, have a planet that exists in the so-called habitable zone of its star. Just the right distance from the star to have liquid water on the surface. So really everything that we think was necessary for life to begin on Earth is all over the place. Simultaneously, our capability to search for that life, both in terms of SETI and in other ways, is dramatically expanding. And we'll talk a little bit more about that as the talk goes on. But again, just to reiterate, simultaneously we know that there's a very, very high likelihood that all of the stuff that we think was necessary for life to exist exists elsewhere, and our capability to explore it is only increasing. So since this is a talk at the SETI Institute, I cut probably 95% of the introductory material from my slide deck, but I will just take a minute to talk a little bit about the background of SETI. As many of you know, in SETI we don't directly search for intelligent life. We don't have any way of directly detecting intelligence. So we use technology as a proxy for intelligence. And our own technology here on Earth has been producing detectable emission that we could detect at interstellar distances for about the last 100 years or so. And these include things like radar signals and narrowband signals from terrestrial radio transmitters, but also optical transmissions. We don't do this a whole lot now. We're starting to do more of it. But it's quite an amazing fact that if you pair our most powerful lasers, this is actually an image from the laser at the National Ignition Facility in Livermore. If you pair something like this, very powerful pulsed laser, with a very large diameter mirror, like something we might have at the KIC telescope, that laser emission could outshine our star at 1,000 light years by many orders of magnitude. Just to put a bit of a finer point on some of the radio examples of our own technology that could be detected in a SETI experiment. This is the brightest terrestrial radio transmitter. It has a 2 megawatt transmitter at S-band. And this could be detectable across the galaxy with the kinds of searches that we're going to talk about today. There's also other examples. This is called the United States Space Fence. This is actually defunct at the moment, but a new version of it is going to be built. This is slightly less power and a commensurately lower equivalent isotropic radiated power, so a lower kind of luminosity or pseudoluminosity, if you will. But it has a fan beam, so a much larger beam on the sky. So oftentimes when we talk about Arecibo, the electrical engineers in the room are quick to point out that, well, yeah, it's very, very bright, but it gets that high brightness from having a very, very large gain, which means it has a very small beam on the sky, which is absolutely true. So the chance that we would intercept a signal from Arecibo if we sort of put one at a long distance is perhaps low. But there are other transmitters that we use for other purposes that have much, much larger beams, search radars. And these kinds of things would be much easier for us to detect statistically in the searches that we do. And those are just a couple of examples. There are a few transmitters that have luminosities that are similar to Arecibo. Arecibo is not the only planetary radar that we have. There are perhaps a dozen very, very long-range aircraft radars that we could detect out to a few hundred light years, and of course hundreds of these high-power TV and radio stations that we don't yet have the sensitivity to detect those, but with some of the telescopes that we're building in the next couple of decades, I think that we will. And just in case you didn't believe me about what I said about the laser at Livermore and the fact that it could outshine the sun, I put kind of some little nerdy details here. You get something like 5 photons per nanosecond per meter squared at 1,000 light years from a 5 megajoule pulse laser and a 10-meter reflector. And that compares to about 10 to the minus 3 per nanosecond per meter squared that you would get from a solar-type star at 1,000 light years. So indeed, several orders of magnitude, something like this could outshine the sun. So, in SETI in general, but certainly at our group at Berkeley, we follow the philosophy that we really don't know where on the electromagnetic spectrum we might expect to detect evidence of extraterrestrial technology. And very smart people could come up here and could tell you all kinds of reasons why we should look at very low frequencies or maybe mid-frequencies and the terrestrial microwave window, the water hole maybe around 21 centimeters, maybe higher frequencies if they're using microwaves to propel spacecraft or if they want to transmit a lot of information, maybe mid-infrared if they want to get through the dust, or maybe optical if, again, they want to transmit a lot of information. But we really don't know. So just in general, our philosophy in our group is to do experiments across as much of the electromagnetic spectrum that we can access from the surface of the Earth as we possibly can. What you see here is a plot of atmospheric opacity versus wavelength. So these little windows here just indicate where in the electromagnetic spectrum radiation gets through our atmosphere, and in the case of very, very low frequencies, gets through our ionosphere. So over the course of the talk, I'll talk a little bit about several experiments that we're doing across the electromagnetic spectrum here. Again, just trying to probe as much of this spectrum and for as many possible different signal types as we can. This is one of our favorite telescopes. This is the Arecibo Observatory. Earlier I mentioned that there's a very powerful transmitter on here, but it's usually used just to receive radiation. This is a very, very famous radio telescope. It featured heavily in the movie Contact and also several other movies. And we've been doing SETI here for some time. We spend a lot of time using this receiver called the Arecibo L-band feed array. It has 7 pixels on the sky. So usually with a single-dish radio telescope, you can only look at one position. But with the alpha receiver on Arecibo, you can look at 7 different positions at once. It has about a 300 megahertz bandwidth. And something that's going to be very important for the kind of SETI that we usually do at Arecibo, it's often used for surveys. So at our SETI experiments with Arecibo, we observe in what's called a commensal or a piggyback mode. Time on Arecibo is very, very oversubscribed. It's very, very expensive. And so it's hard to get a lot of time just to do SETI. But we've figured out a way that we can piggyback our observations on top of all the other astronomy that's going on with the Arecibo telescope. So while other people are doing surveys for neutral hydrogen or looking for pulsars or quasars, fast radio bursts, whatever they're doing, we can get a copy of the signal that comes from the receiver, and we can analyze it completely independently. And this is actually something very special about radio telescopes. Because of the way that radio telescopes work, we can amplify the signal a lot right when we get it at the receiver, and we can send it to as many different instruments as we like. So you can't do that with an optical telescope. If you want to have 2 instruments connected to an optical telescope, you have to split the light path, and one instrument gets half the photons and the other instrument gets the other half. But with a radio telescope, we can copy the data, and we can send it out digitally or as an analog signal ad infinitum. And this is what really enables us to do some very fantastic work with Arecibo. This is what our commensal SETI system looked like in Arecibo in 2012. This is a picture, a little diagram of that alpha receiver that I told you about. We connected it to an analog box that actually split out all the 14 signals, 7 beams times 2 polarizations that comes from that receiver. And then we fed it to a digital gadget that we put together that was mostly made up of something called field programmable gate arrays, and then did a high-resolution spectroscopy search. And I'll show you a little bit of the data from this as we move on. A couple of things I want to point out about this. It's all FPGAs and basically just a computer for monitor and control. And then the other thing is that we're only able, with the system that we had in 2012, to look at one of those signals at one time. So the 14 signals, again, 7 beams times 2 polarizations, those are time multiplexed through our instrument, and we can only look at one at once. And those 2 things will contrast with the next version of this instrument that I'll show you in a bit. So here's the sky coverage that we achieved from 2009 to 2012. We got about 6,000 hours on the telescope. The very sort of strong shape, you see this, what's indicated here is the total number of hours times the solid angle on the sky that we observed. And the shape that you see here just reflects the very limited area of the sky that the Arecibo telescope can see. So it's a great telescope. It's incredibly sensitive, but just simply because of the way that it's built, it's not able to see as much of the sky as we would like. And again, we'll talk a little bit about some of the ways that we're ameliorating this problem with SERENDIP as we go on. So SERENDIP is an experiment that's been around for a long time. I saw a great SERENDIP shirt that someone had on down here. It's been around since before I was born, in fact, at Berkeley. It was the very first SETI experiment that Jill Tarter worked on. Something very, very special, I think, and I'm sure just about all of you know who Jill is. The first version of the SERENDIP experiment was deployed at Hat Creek Observatory, which is actually the home of the Allen Telescope Array, so lots of little insular connections here in the SETI field. And we moved on to SERENDIP 5.5. That's the version that I showed you at Arecibo, and now SERENDIP 6. That we'll talk a little bit more about that we just deployed in the last couple of years at both Arecibo and the Green Bank telescope. And I think something that you'll see here if you're certainly a Microsoft employee is that there's a very close tracking of Moore's law growth here in the capabilities of SERENDIP instrumentation. In SETI in general, especially in radio SETI, the capability of our instruments are really directly hinged to Moore's law growth in electronics. As computers become twice as fast, 10 times as fast, 100 times as fast, the amount of bandwidth that we can search in our experiments increases by a commensurate amount. And that enables our searches now to be many, many orders of magnitude more powerful than they were in the past. And I think in a very real sense, in the next couple of decades, we're going to get to the point where computers will be fast enough that we can search essentially all of the radio spectrum that's available to us on the surface of the Earth. And that will be a very, I think, special time in terms of SETI in general, and that really for the first time we'll be able to do a truly inclusive radio search. So I talked a little bit about this already, but I'll mention it again. The kind of analysis that we do in SETI is very, very computationally intensive. It requires very, very high-performance computers, huge data rates. We want to search lots of different types of signals. And all of this requires very, very high-performance computers and very flexible computers that enable us to do the very different kinds of searches that we want to do. And it often requires high-performance custom instrumentation. So to take kind of a step back here, historically, if an observatory wanted to build a new instrument, if a new radio observatory was constructed, the way that would work is that the team designing the observatory would hire a bunch of electrical engineers, bring them all together in a room, and they would design the digital backend, the digital instrumentation for the telescope from the ground up. And these experiments were characterized by very, very large non-recurring engineering costs. And they took a really, really long time, maybe 5 to 10 years. And so by the time this custom gadget that these very, very smart electrical engineers put together got onto the telescope, it was a dinosaur. And just because of the very, very rapid growth in electronics, this system of design ended up putting instruments on the telescope that were far less capable than they really should be, given the very rapid growth in electronics. At Berkeley, we have a group called CASPER, led by Dan Wertheimer, who some of you may know, that is trying to upend, and in fact has really upended this paradigm in digital instrumentation development for radio astronomy. So what we've tried to do is leverage a lot of the ideas that are driving developments in Silicon Valley today. Modular hardware, reusable gateware, and software. We want the same instrument design that we designed 10 years ago to run on computers that we have now 50 or 100 times faster. We want everything to be open source. Nothing proprietary, no proprietary protocols, no proprietary software. Everything is shared with the community so everyone can benefit from what everyone else is doing. And we also try to incorporate commodity elements into the instrumentation pipeline wherever we can. And what that enables us to do is upgrade the instruments very, very easily. If most of our computing, for example, is done on multi-core processors or graphics processing units, when NVIDIA releases their next version of GPU or Intel releases their next version of CPU, we can plug those things into our instrument and immediately get much, much more capability out of our instrumentation. And this is sort of what this whole thing looks like when you string it together. It makes a radio astronomy instrument, something that's a little bit baroque, even for someone that's technically inclined, look a lot like a Linux cluster. So here you see just a 10 gigabit switch that's serving as the interconnect between a whole bunch of compute elements. We have some FPGA boards. These are our custom FPGA boards that we use to actually acquire the digitized data from the telescope, interfaced with commodity CPUs, and then all with open source software running on the board. So the same board that does one thing on one side of the instrument can do something completely different on the other side, simply with reprogramming the software. And what we're trying to do is sort of straddle this, this sort of area between performance and development cost and complexity. Down here you have something like a CPU, your Python code. And up here you have a custom ASIC, a custom integrated circuit, a custom chip. So very, very low development cost and complexity for writing some Python code, but fairly low performance as well, versus very, very large development cost and complexity and commensurately very, very high performance from something like an ASIC. So what we want is to give up a little bit of performance, but make up dramatically in terms of development cost and complexity. And the really, really cool thing that this does is not just make the instruments cheap and make them easier to build, but it actually allows the astronomers to build the instruments. And that's a really very, very important thing, because the astronomers are the ones that know what might be gained by going to shorter and shorter integration times, or getting higher and higher spectral resolution, or looking for some new kind of signal. They're the ones that are best suited to be able to answer those questions. And if they're the ones that are designing the instrument, then the scientific questions that will be answered from those kinds of developments happen much more quickly. Taking all of those concepts into account, this is what we've ended up with our latest commensal deployment at Arecibo. This is Serendip 6. It's a sort of similar diagram to what I showed you before, but rather than having some analog switch that time multiplexes all of the outputs from this receiver, we feed them into a couple of these FPGA boards. They send just digitized data into a 10 gigabit switch, and then we have a huge cluster of commodity compute nodes equipped with GPUs that do all the SETI signal processing. And this latest deployment also allows us to do something very, very cool, which is in addition to doing SETI, so here's the Serendip 6 part of the instrument over here, we have another bit here that's labeled Artemis. What this part of the instrument is doing is actually searching for something astrophysical, fast radio bursts. This is a new class of fast radio transient phenomena that we think probably comes from magnetars or some kind of exotic pulsars. And we're able to simultaneously search for those as we're doing SETI. So we can do both at the same time. And again, everything is connected in the same fabric to a 10 gigabit switch. So just one digital data stream feeding right now two, but maybe many different science pipelines. And here's what this thing looks like. If you go to enough radio astronomy talks, you'll see lots and lots of these racks. It really wouldn't be a complete talk if I didn't show you a rack of computers. And this isn't the last one that you'll see in my talk. But we're very, very proud of it. Moving on to another telescope, this is the Green Bank telescope. This is in West Virginia, another telescope that we've just started using really in the last couple of years. Our very first experiment just started in 2011, and this was actually just a year after the 50th anniversary of Frank Drake's very first SETI experiment at the Green Bank Observatory. And this experiment was conceived of on a plane with myself and Jill Tarter and Dan Wertheimer coming back from a meeting at Green Bank to celebrate the 50th anniversary of Project Ozma. So it's a very, very special experiment for me. We did a total of 24 hours of observations of the Kepler field. We did targeted observations for about 12 hours of 86 of the most habitable-looking planet candidates that had been found by Kepler at that time. And we also did an 11-hour raster scan of the entire Kepler field. And this experiment really has set the stage for the kind of analysis and the kind of experiments that we're doing with Breakthrough Listen that we'll talk more about towards the end of the talk. So we published one paper a couple of years ago based on our analysis of the targeted observations. Less than 1 in 10,000 solar-type stars were found to have transmitters brighter than what we have on Earth. And less than 1 in a million stars hosts a super civilization with very, very bright monochromatic radio emission. And those might not sound like particularly impressive numbers. They're not the greatest limits. But I think they're very important in SETI in that they are actually limits. We did a fairly rigorous statistical analysis of our data to come up with these. And this is the direction that, philosophically speaking, that we're very much trying to push SETI towards. Even though we're searching for a needle in a haystack, we should be very, very careful about reporting what part of the haystack we're looking at and what kind of needles we looked for and whether or not we found them. And again, philosophically speaking, a direction that our group is really trying to go at Berkeley. So we have a couple of projects in prep using these same data. We have a graduate student at Berkeley named Isaac Shivers who's doing a machine learning-based search on our raster scan data, searching for narrowband emission. And a former undergraduate who's now a UCLA graduate student named Abhimat Gautam, who's doing a search for individual pulses in our raster scan data. And for those of you that are familiar with searching for single pulses, Abhimat is doing something pretty cool in his analysis. He's not just looking for positive dispersion measures. This is a plot of dispersion measure versus number of candidates. This is essentially a measure of the column density of interstellar plasma between us and the source. He's not only looking for the physical kind of dispersion, but also the negative aphysical kind of dispersion, which has been suggested a very advanced civilization might deliberately imprint on a single pulse signal that they sent out to distinguish it from a natural signal. So this is, as far as I know, one of the first searches that includes negative dispersion measures. And both of these works are fairly well along and should be published pretty quickly. So independent of Breakthrough Listen, I think many of you probably know that the Green Bank Telescope is part of Breakthrough Listen. We've been doing additional SETI with the Green Bank Telescope. We have a project where we were awarded 36 hours of time to look at exoplanet conjunctions. So this is something that we can do now that we know of many, many multi-planet systems from the Kepler mission. We can time our observations for when two planets are aligned relative to the Earth. And the idea here is that if a very advanced civilization proceeded on a technical development similar to our own, perhaps the first thing that they might do is colonize multiple planets in their own system. And then there would be quite a lot of communication, we think, between those two planets. So it stands that if we observe the system when those two planets are aligned, we have a greater probability of intercepting some leakage that might spill over this planet as this planet is transmitting towards it. We're also including observations with the GBT in a campaign that we call Panchromatic Observations of Nearby Stars. This is a broad, multi-year effort that our group is undertaking to observe the 50 or so stars, maybe 70 stars that are within 5 or 6 parsecs of the Earth with all the different telescopes that we have available to us. So one sort of concrete set of stars that we've examined with every technique, literally, that we have available to us in SETI. And here's a very similar plot to the one that I showed you before from Serendip 6 on Arecibo. So when you start building things out of 10 gigabit switches and computers, it's quite easy to make copies of them. So the downside to that is that you get twice as much data, or maybe 4 times as much data, which turns out to be quite a problem eventually. But the nice thing is that it's easy to deploy additional copies. So we've taken basically everything that we've done at Arecibo for Serendip 6 and just duplicated it for Green Bank. So now we have a fully commensal system available to us at Green Bank. Anytime anybody is doing anything on the Green Bank telescope, we can analyze the signal that the telescope is producing for evidence of extraterrestrial intelligence. And here's some very early data from this project. This is led by an undergraduate at Berkeley named Kyle Archer with help from a number of others. And Kyle is just starting to produce histograms of the number of hits versus power, time, and fine channel number. These are plots that will be very, very familiar to people that are involved in radio SETI. And probably what most of you see here is the same thing I do, which is lots and lots of interference, which is, of course, the biggest challenge in radio SETI. And again, these observations are from L-band, from 1 to 2 gigahertz. But this system that we have at Green Bank is actually capable of doing observations with any receiver that's in the focus of the telescope. So we also recently started doing some work with a really cool telescope in Europe called LOFAR. This is the low frequency array. It's made up of a whole bunch of these dipole stations. This is a high frequency component of LOFAR that operates from about 100 to 200 megahertz, and a lower frequency component that operates from about 50 to 100 megahertz. And these stations are located all over Europe, mostly in the Netherlands, but all over Europe. And the entire telescope is built inside of a supercomputer. Initially, in fact, all of the digitized signals from all of these dipole antennas that are fixed on the ground were actually fed literally into a Blue Gene supercomputer. And the entire telescope was basically constructed inside the supercomputer. And so the really cool thing that you can do if you have a telescope that's built this way is that you can have a huge amount of flexibility in the way that you combine the digitized data from all of the different antenna elements. So you can build a big wide beam like this with fairly low sensitivity, or kind of intermediate beams like this with more sensitivity but still a fairly large solid angle on the sky, or very, very fine, very high sensitivity pencil beams, all depending on the way in which you phase up the signals that come from each one of those telescopes. And it allows a huge amount of flexibility in the way that you construct the instrument, but also a huge amount of flexibility in the way that you do SETI. And of course, a telescope like this is very, very amenable to these piggyback or commensal observations that I talked about, but we haven't yet done that with LOFAR. What we have done is begun to develop a multi-beam SETI pipeline. And if you've heard Jerry Harp or maybe Seth or Jill talk about how the ATA does SETI, this concept will be familiar to you. Basically, if you form multiple beams on the sky, you can use the fact that you have information from multiple sky positions to weed out the things that are coming in from the side lobes of your telescope, or conversely, identify those things that are coming from only one place on the sky. And here's just an example of that. So here's a configuration in which we're forming 8 beams with the LOFAR telescope. 7 of them are on nearby stars. These are supposed to be M-dwarfs. And one of them is on a pulsar. So here we see the signal from this beam and this beam. We see that the pulsar is detected very, very strongly in the beam that's pointed at the pulsar, which is good. It's not detected at all in the beam that's not pointed at the pulsar, also good. But then we see this narrowband feature here. This is a high-resolution 1 Hz spectrum from this telescope. And we see it's detected at both the beams. So, and this is, of course, some interferer. So the interference shows up in both of the beams, and the astrophysical thing in this case, but importantly, the thing that's isolated on the celestial sphere, the thing that's only coming from one place, only shows up in one of the beams. So this is a very, very powerful SETI technique, something that you can do with modern radio telescopes, and this is what we've put together at LOFAR. This project is led by Emilio Enriquez, who's a PhD student who's just finishing up at Nijmegen in the Netherlands. And I think all of you from the SETI Institute should be very, very proud that Emilio Enriquez was actually an REU student in your REU program back before he started a PhD program at Nijmegen. And if any of you know who Heino Falke is, Heino Falke gave a talk to you guys and recruited Emilio out of your REU program. And now he's doing really a world-class SETI experiment for his PhD thesis at Radboud. So you should all be very, very proud of that. What Emilio's doing is looking at the 30 nearest stars to the Earth. This is part of that panchromatic SETI campaign that I talked to you about. And his analysis is probably about 50% done, but he's supposed to finish in June, and so he's got to have it finished by then because he's got to put it in his thesis. So I wanted to take just a couple of minutes to talk with you about laser communication. I know that you had Shelley Wright come out and talk with you a little bit about her optical and near-infrared SETI project. So I'll just mention it briefly. Here's Shelley at the Lick Observatory working with the Nickel telescope when she was still a graduate student. So why might we want to, one, look in the optical, and why might we want to extend that into the infrared? Well, so really the very special thing about optical is that you can get a huge amount of information in your signal. So if a very advanced civilization either wanted to intentionally transmit a lot of information to us, or they wanted to have a signal for their own purposes that contained a lot of information, then using very, very short wavelengths or very, very high frequencies is a really good idea. But there's a problem with that, in that there's a lot of dust within our galaxy. So if we wanted to look for these signals from really far away, we would have a problem because the dust would itself attenuate the optical radiation quite a lot. Well, it turns out that if you just go to wavelengths that are a little bit longer than optical light, so maybe 1,000 nanometers or 1,200 nanometers, just into the near-infrared, you can get through that dust. The amount of absorption that you see from the dust is a very, very strong function of the wavelength of the light. So you go to just a little bit longer, and you can get a lot more of it through the galaxy. And so thanks to some brand new detectors called avalanche photodiodes that are sensitive in this part of the electromagnetic spectrum, Shelley's put together a fantastic experiment that's one of the first near-infrared SETI experiments ever. It's sensitive to very, very brief flashes of near-infrared light. This is a slide that's probably from maybe the middle part of 2015. This experiment is now completely robotic. It's completely unmanned or unwomaned, as the case may be. And it observes something like 5 days a month, 6 days a month, something in that nature. And we're thinking about some upgrades to this system. So as it stands, we actually have that instrument just connected to very simple oscilloscopes that record the signals that come from the APDs. But what we'd like to do is hook these up to some fancier set of digital electronics that will enable us to, one, look for a lot more different types of signal types. We can integrate for longer. We can do Fourier analysis of the signals that come from these photon counters. But we could also expand the system to maybe include optical photomultiplier tubes as well. So we could have a dichroic where we send some of the light, the near-infrared light, to one set of analyses, and the visible light to another set of photon counters. Again, so that we can search more and more of the electromagnetic spectrum. So just a kind of a transition now from the stuff that exists now to the stuff that's going to exist in the future. Hopefully many of you are aware of the Square Kilometer Array project. This is an international effort to build a radio telescope with a square kilometer of collecting area. Make it something like 20 times as sensitive as our most sensitive radio telescopes that we have now. Unfortunately, the United States is not a partner anymore in the Square Kilometer Array project. This is an animation of what we hope the Square Kilometer Array will look like in South Africa. It's actually made up of two components at present. There's a mid-frequency component that looks a lot like the Allen Telescope Array, and in fact borrows a lot from the technology development that came from that project, and a low-frequency component in Australia. Again, the sort of scheduled date is 2018 to 2023. The first phase of the project has been cost capped at 650 million euro. Again, I'll mention that the United States is not a partner, unfortunately. About 30% of this has been committed to the project, and the remaining 70% is still being solicited from the national partners. The mid-frequency component here in Southern Africa is going to be sensitive from about 350 megahertz to 14 gigahertz, 5 times more sensitive than the Jansky VLA, which is really the canonical world-class radio telescope that we have today. And the low-frequency component in Australia, 50 to 350 megahertz, and 10 times as sensitive as LOFAR, the low-frequency radio telescope that I mentioned to you that we're using earlier. And this is phase one of the project. So if you notice a discrepancy when I said 20 times as sensitive as our best radio telescopes and what you see now, that reflects that this is the first phase of construction of the Square Kilometer Array, not the second phase, which would actually build it out to a full square kilometer of collecting area. So again, just to illustrate where those frequency bands fall, here's the SK low band and the SK mid band, completely covering this entire terrestrial microwave window, although not simultaneously. This is covered in several different receiver bands, probably 4 bands when all's said and done. So there are a number of ways you could divide SETI experiments. One way is to think about SETI surveys and targeted SETI and data mining SETI. SETI surveys where you look at a very, very large patch of the sky. Targeted SETI where you look at individual objects that you think are likely hosts for intelligent life, or data mining SETI where you look at data that's already produced by an astronomical instrument that's used for other purposes. SKA1, the first phase of the project, is probably going to be mostly targeted SETI and data mining SETI, simply because the computational capacity that we have is not going to catch up in time for us to be able to do truly large sky surveys with the Square Kilometer Array version 1. But with SKA2, maybe in 20 years, we might have the computational capacity to search over the entire field of view that telescope sees. We're envisioning something like a 1 million target catalog for our experiment on SKA1, made up of all the kind of usual suspects in SETI, nearby stars, sun-like stars, kind of Habcat kind of stars. known Earth-like exoplanets and solar system-like exoplanets. It seems like every month when we pick up the newspaper, we hear about a planet that's more and more like the Earth, or a planetary system that's more and more like our own solar system. That's, of course, going to continue. And pretty soon we're going to have an analog for our own solar system that's probably at the 1 or 2% level. And, of course, that'll make a very, very good SETI target. We already talked about serendipitous alignments. This is certainly going to be a part of our program on the SKA. And also other kind of more, I'd say, kind of skeptical phenomena that we might explore. And one of my favorite examples of that is something called a natural maser. So these are astrophysical sources that result in very, very narrow band radio emission, not quite as narrow as we search for in SETI. But because of the physics of the way that the gas that produces that emission is set up, it could be used as a natural amplifier. So a fairly advanced civilization could use that to dramatically amplify a signal that they wanted to send to other life. And so we might include those kinds of things or ideas along those lines in our searches with the SKA. There's also going to be a tremendous amount of synergy with our work on the SKA. There's going to be a lot of new space missions that are going to provide us great targeting information. The Transing Exoplanet Survey satellite is going to find many, many planetary systems very close to the Earth. And of course, Gaia is going to give us a catalog of stars, something like 1 billion objects. So we'll have more than enough targets to keep us busy with the SKA. Just a couple of kind of bullet points. The most thorough conducted SETI search previously was Project Phoenix, 1,000 stars to a luminosity limit of about 2 × 10 to the 19 ergs per second. SKA-1 in a 5-year commensal campaign could survey every star within 200 light years, every single star in the part of the sky that it can see, to a luminosity limit an order of magnitude fainter. And SKA-2 could, in about 10 years, could survey every star within 200 light years to a luminosity limit equal to our aircraft radars over the entire terrestrial microwave window. So very, very powerful telescopes, and we're very, very hopeful that they'll eventually get built. And this is just a graphical representation of what I just told you, which you probably could have figured on your own. You build a telescope like SKA-1 or SKA-2, and you're going to have a dramatically sensitive, very, very powerful SETI instrument. So I'm running a little bit short on time, so I think I will skip through a couple of these slides. So that in addition to SKA-1, SKA-1 mid and SKA-1 low, there are so-called pathfinder and precursor facilities that are coming online, including the FAST telescope in China, that are themselves fully funded and are absolutely going to happen and will be fantastic SETI instruments in their own right. And we're very excited to get going on these as soon as we can. Meerkat is going to be released for early science in probably June of this year, and will be fully built out, basically a southern version of the Jansky Very Large Array in probably mid-2017, something like that. MWA is completely finished now with 128 of these tiles, about a third or so the sensitivity of that low-frequency array telescope in Europe, and will be doubled in collecting area over the next couple of years. And of course, the monster in the jungle in southern China, FAST, 500-meter single dish, Super Arecibo, the most sensitive telescope in the entire world, is expected to be completed in the next 18 to 24 months. So we have a working group for Cradle of Life Science that I'm the co-chair of, along with Di Li in China, who's the principal scientist for the FAST telescope. The membership is open, so if you're interested in getting involved in Cradle of Life Science on the SKA, please contact me. And also there's a SKA Young Scientist meeting in India. If you're a young radio astronomer, I know there's at least one in this room, and you're interested in SETI on the SKA, this is a great opportunity to voice your support. So I wanted to maybe just take a couple of minutes for a small digression before I talk about Breakthrough Listen, to just talk about facility radio experiments. So this is the Arecibo telescope. I already told you all about this. You guys have seen this a few times. This is a very famous telescope in SETI. It was home to quite a lot of the Project Phoenix observations, again, the world's most sensitive and comprehensive search for extraterrestrial intelligence. If you Google radio telescope SETI, you'll see, well, here's the ATA, but there's quite a few pictures of Arecibo. It's a radio telescope that in many ways, at least in the public's imagination, is synonymous with SETI. This is the SETI telescope. If you're interested in using this telescope, there's a document you can download. It's called the Astronomy User's Guide, Astronomer's Guide to the Arecibo Telescope. It's, I don't know, about 150 pages or so. Here's the introduction. If you read through it, there's all kinds of instructions in it for doing, here are the different signal processors available. If you want to do continuum observations of a quasar or something like that, here's how you do it. If you want to look at a pulsar, here's what instrument you use, and here's how to analyze your data. If you want to look at spectral lines, if you want to look at hydrogen or hydroxyl, here's how you do all of that. So if you download this thing and you run this little Unix command, which many of you will appreciate, this is what you get. And this is a problem. So we know how to do SETI at the SETI Institute, and we know how to do SETI at UC Berkeley, but the rest of the world doesn't in many respects. And there's many people in the astronomy community that would like to do SETI that are unable to because simply there is no manual, there is no guide to doing SETI observing. So just to kind of reiterate that again, here's an excerpt of a paper from something called the Targeted Search System, which was part of Project Phoenix, and I promise I'm not picking on Project Phoenix. But here's a line from it that I really liked that kind of illustrates what usual SETI instrumentation is. TSSs are designed to be transportable via a custom shipping container on military cargo aircraft and special flatbed trucks. This is the kind of equipment that is not normally available to astronomers that want to do a new kind of experiment. So we're developing what we call facility SETI observations capability, the ability for just regular people that use the telescope to do SETI experiments with these telescopes. We'd like people to be able to do it on all of these other telescopes. And this is a big part of what we're doing at Berkeley to build an open source SETI analysis toolkit, a set of software tools that can be used to do SETI with radio telescopes all over the world. We're very interested in using open source tools like Jupyter and Docker and AWS and Google Cloud Platform and maybe even IBM Spark, Graham, depending on how things shake out. And we'd love to have collaborators on this. So if you're interested in open source signal processing, open source time series analysis, especially with applications to SETI, please get in contact with us. So last but certainly not least, the Breakthrough Listen initiative. The world's most sensitive, intensive, and significant SETI experiment to date. In addition to all of the regular analysis that we're going to do in Breakthrough Listen, the traditional SETI analysis, everything about this project is open source. All the data are open to the public. If you want to get involved through SETI at Home, that's something that is certainly available. This is a brand new version of the SETI at Home screensaver that for the first time ever is processing data from a telescope other than the Arecibo Observatory. We're going to look at 1 million stars, do a complete survey of the Milky Way galactic plane and 100 nearby galaxies. And this is kind of marketing speak, but it's accurate, and I think it's important. A day of Breakthrough Listen is 1 year of any previous search. And this really comes from two things: the world's largest, most sensitive radio telescopes, and Moore's law growth in electronics, which brings to bear the most powerful instrumentation that we've ever had in SETI experiments to do the search. And we're going to make more scientific data publicly available than any other project in history. Exactly what this number is something that we're working with our colleagues in Silicon Valley to determine. But it's going to be an awful lot of data, and we're going to need an awful lot of help. And we're going to ask the public. In fact, we already have asked the public for help in this. There are 3 telescopes that are so far announced as part of the Breakthrough Listen initiative. The Automated Planet Finder at Lick Observatory near here, just near San Jose. This is a telescope that's primary mission is to search for extrasolar planets by looking for the wobble in their spectral lines, the so-called radial velocity method. But because it has this very, very high-resolution spectrograph that's used for that purpose, we can also use it to search for very, very narrow laser lines, artificial laser lines that might be produced by a technological laser. Also, the Green Bank telescope, which we've already talked quite a bit about, we have about 20% of the time on the Green Bank telescope. And one thing I didn't mention about the GBT, which is a very important part of it, 2 things actually. One, it's located in a federally protected radio quiet zone. So it's actually in a part of the country that's federally protected from the effects of harmful radio frequency interference, at least to the degree that that's possible. It also has very, very broad frequency coverage. So we've talked about observing over the terrestrial microwave window, which is generally thought of to be about 500 megahertz to 10 gigahertz or so. The GBT is actually sensitive up to 100 gigahertz. So for doing targeted observations of nearby stars, if you want to look at a lot of the electromagnetic spectrum, the Green Bank telescope is a great telescope to do it with. Also, the Parkes telescope, we have about 20% of this one as well. And this one has a multi-beam receiver very similar to what we have on Arecibo, but it has 13 beams rather than 7. So the fact that it's a smaller telescope, it's only 64 meters, that naturally gives it a larger beam. And the fact that it has a 13-beam receiver rather than 7 makes it much, much better, even than Arecibo for doing sky surveys, which is going to be its primary contribution to the Breakthrough Listen effort. Lots of technology here. We've already talked about some of this. Our systems at Green Bank are going to be capable of recording about 350 to 400 gigabits per second, similar kinds of data rates at Parkes, all GPU accelerated, 10 to the 10 channel spectroscopy, 10 billion channel spectroscopy. Again, I already mentioned this, a very nice, brand new state-of-the-art high-resolution optical spectrograph present at the Automated Planet Finder for doing optical SETI work. Here's a timeline of the project. It was announced in July, and we started work in August of 2015. We began observations at APF in November and observations at GBT in January of 2016. And we'll begin at Parkes in October. That's a pretty tight timetable. Our chief engineer, David McMahon, made up these fun slides about how to build a SETI instrument in 6 months. You use a bunch of existing stuff. You install a big compute cluster. And then you use existing software where you can, stuff that's been developed for other purposes. You integrate with the monitor and control system, and you get first light. This is an observation of Voyager. And this is an observation of an astrophysical source, a pulsar. So it's really an incredible feat that we were able to do this in only 5 months. And we did it thanks to all of that really Silicon Valley style instrumentation development that we talked about in the earlier part of the talk. We're very interested in looking for a wide variety of signal types in addition to just the traditional narrowband and Doppler drift searches that are usually done in SETI. We'd like to do wideband analysis. This is a plot from a colleague of ours, Ian Morrison, in Australia, that illustrates the detection of a BPSK signal, a rather common digital modulation type in a power spectrum, just a Fourier analysis versus an autocorrelation analysis. And indeed, it's much easier detected in the autocorrelation analysis, but autocorrelation is not commonly part of SETI searches yet. We're also interested in machine learning, and we have a student, as I mentioned, that's working quite a lot on this. So I'll just sort of end my talk here, and I'll let this fun little graphic that we had made for Breakthrough Listen play in the background while I maybe take a couple of your questions.